The silence after December 19th was louder than any signal we could have received. You watched the coverage fade, the headlines moved on, the countdown clocks disappeared from your screen, the interstellar visitor passed by, invisible to your naked eye, and the world exhaled. Just a comet, they said, just ice and rock, tumbling back into the dark. Nothing happened, nothing changed, but the telescopes never stopped tracking. While you were told to move on,
Trajectory stable, T-minus 5 minutes to insertion
new data,
burn.
new measurements, new questions that sound less
All
like
systems
astronomy
reporting
and more like
green.
logistics, because they are no longer asking what this object is. They're asking what it was doing here, and more importantly, what it's carrying away. What if December 19th wasn't a close approach? What if it was a pickup? And what if the brightest minds on Earth are now racing to answer one question? Do we try to catch this thing, or do we destroy it before it reaches Jupiter? Welcome to the story they're not showing you on the news. This is unfolding in real time. And the next major event is March 16th, 2026. If you want to track what happens at the Jupiter rendezvous, make sure you're subscribed with notifications on. This isn't speculation, it's following the actual data as it comes in from observatories around the world. Let's walk through what they're seeing. Let's start with what you were supposed to see. December 19th, 2025. The day marked in red on every astronomy calendar for months. The Day 3 ice/Atlas would make its closest approach to the Sun. Swinging through our inner solar system at a distance that sounds safe on paper, but feels uncomfortably close when you're talking about an object we still don't fully understand. The media had their cameras ready. The conspiracy theorists had their predictions locked and loaded. And maybe you stayed up late, refreshing the live feeds, waiting for something, anything, to happen. And then, nothing. The object passed. The Earth kept spinning. Your morning coffee tasted the same as always. But here's what they didn't show you in those news segments. Here's what happened in the 48 hours after the cameras turned off. The object didn't slow down. It didn't change course. It didn't fire off any dramatic signals that would make for good television. What it did was something far more subtle, and in the eyes of planetary scientists, far more disturbing. It accelerated. Not much. We're talking about tiny variations in velocity, the kind of change that requires weeks of careful measurement to even detect. But it was there. Dr. Davide Finocchia at NASA's Jet Propulsion Laboratory was one of the first to notice it in the tracking data. The object's trajectory after perihelion, after its closest approach to the Sun, showed what astronomers call non-gravitational acceleration. That's a careful way of saying this thing is pushing itself in ways that gravity alone can't explain. Now, before you jump to conclusions, comets do this all the time. When ice sublimates, when frozen gases turn directly into vapour under the Sun's heat, that venting creates thrust, its natural rocket propulsion. We've seen it on Halley's Comet, on Comet Neo-Wise, on dozens of others. The ice heats up, gas jets out, the comet gets a tiny push, physics as usual. Except 3I/Atlas was already moving away from the Sun when this happened. Think about that for a second. Comets vent most aggressively when they're getting closer to the heat source, when the Sun's radiation is intensifying, when the ice is being bombarded with more and more energy. They don't usually wait until they're leaving, until they're heading back out into the cold, to suddenly start pushing harder. It's like watching someone turn on the afterburners after they've already passed the finish line. The velocity increase was measured at approximately 0.3 millimeters per second per day. That number probably doesn't mean anything to you. And honestly, it shouldn't. It's incredibly small. But here's the context that makes it strange. Halley's Comet, one of the most active, well-studied comets we have, shows similar non-gravitational effects, but they follow a predictable pattern tied to solar heating. The closer Halley gets to the Sun, the stronger the push. The farther away, the weaker it becomes. 3I/Atlas is doing it backwards. Dr. Matthew Knight, a comet specialist at the USAS Naval Research Laboratory, published preliminary notes suggesting that if this acceleration is purely from outgassing, from natural ice sublimation, then the object would need to be venting from specific regions on its surface, regions that only became active after perihelion. Possible? Yes. Typical? Not even close. And here's where the timeline gets interesting. Let's compare this to another interstellar visitor. One you might remember, Oumuamua. That object, the first confirmed interstellar traveller we ever detected, also showed non-gravitational acceleration. It also confused scientists with its trajectory. And it also left our solar system with more questions than answers. The difference is, Oumuamua was small, tumbling, and gone before we could get a good look at it. 3I/Atlas is still here, and it's not tumbling, it's oriented. The light curve data, the pattern of how bright the object appears as it rotates, shows remarkably little variation. If this were a jagged chunk of rock and ice spinning through space, you'd expect the brightness to fluctuate as different surfaces caught the sunlight. But 3I/Atlas maintains a fairly stable brightness profile. That suggests either a very uniform shape, like a sphere, or a controlled rotation, like a gyroscope. Natural objects tend to wobble. This one doesn't. So let's put the pieces together. You have an interstellar object that passed through our system, came closer to the Sun than Venus ever gets, survived temperatures that would vaporize most natural comets, and then, only after it started leaving, began accelerating in a way that doesn't quite match the physics we expect. And it's doing all of this while maintaining a stable, non-tumbling orientation. The official explanation from NASA, the one you'll find in the press releases, is that this is a comet exhibiting unusual but not impossible outgassing behaviour. The Sun heated one side. The rotation is slow enough that we're not seeing much variation, and the delayed venting could be explained by subsurface ice that took time to heat through and reach the surface. All of that is possible. All of that fits within known physics, but it requires a very specific set of conditions to all be true at the same time. It requires the object to be just the right composition, just the right size, with just the right internal structure, rotating at just the right speed. And the scientists who study comets for a living, the ones who've spent decades watching ice behave in space, are starting to ask a different question. Not can this be natural, but what are the odds? Because here's what makes December 19th feel less like an ending and more like a checkpoint. The object is now heading outbound at 60 kilometers per second, faster than anything humanity has ever launched, and it's on a trajectory that will take it past Jupiter in less than 3 months. If there was ever a time for it to do something unexpected, to reveal whatever it's been holding back, the Jupiter approach would be it. The flyby wasn't the event. The flyby was the beginning of the route, and the route has a next stop. There's a particular kind of scientist who looks at a speeding interstellar object and doesn't just see a mystery to solve. They see a bus they're about to miss. Professor Avi Loeb is that scientist, and right now, he's not asking whether 3I/Atlas is natural or artificial. He's asking something far more practical. Can we catch it? You might remember Loeb from the Oumuamua controversy back in 2017. He was the Harvard astrophysicist who publicly suggested the object might be artificial, that its strange acceleration could be explained by a light sail, a giant reflective sheet pushed by starlight. The scientific community didn't love that. They called it speculation. They called it sensationalism. Some called it worse. But Loeb didn't back down. And now, with 3I/Atlas following a similarly strange trajectory, he's not just theorizing, he's proposing a mission, a real, engineered attempt to use this object as transportation, not to study it, to ride it. The logic is uncomfortable in its simplicity. We are trapped in this solar system by distance and time. The nearest star, Proxima Centauri, is 4.24 light-years away. Our fastest spacecraft, Voyager 1, launched in 1977, is currently moving at about 17 kilometers per second. At that speed, it would take roughly 75,000 years to reach Proxima. 75,000 years. Civilization as we know it is only about 10,000 years old. We don't have time to wait for our rockets to get faster. but 3I/Atlas is already moving at 60 kilometers per second, nearly 4 times faster than Voyager, and it's leaving the solar system right now, headed back into interstellar space, possibly toward Epsilon Eridani, a star system 146 light-years away. Loeb's proposal, published in a series of technical notes over the past 2 weeks, suggests we treat interstellar objects not as anomalies but as infrastructure. Think of them as cosmic highways, naturally occurring but usable. He estimates that if we could attach a small payload to 3I/Atlas, something lightweight, durable, and information-dense, it could reach distances in 10,000 years that would take our current technology 30,000 years. That's still a staggering amount of time. Your descendants 400 generations from now might receive a signal from it, but it's 3 times faster than anything we can build ourselves. And more importantly, it's achievable with technology we already have. Now, here's where it gets personal, and a little bit haunting, Loeb has stated, on record, that he would donate his own biological remains to such a mission, his DNA preserved and carried outbound on an interstellar visitor, becoming part of the galaxy's record long after Earth has forgotten his name. It's poetic, yes, but it's also strategic. DNA is information, it's compact. And if there's any chance this object is headed somewhere with receivers, with others capable of reading genetic code, then we'd be sending a message that says we were here, we were alive, and this is what we were made of. But let's talk about the engineering problem, because it's massive. How do you catch something moving at 60 kilometers per second to put that in perspective? The International Space Station orbits Earth at about 7.6 kilometers per second, and docking with it requires precise, computer-controlled maneuvers that take hours. 3I/Atlas is moving 8 times faster, and it's not in a stable orbit. It's leaving. Every second we wait, it's 60 kilometers farther away. Loeb outlines 3 possible approaches. The first is the least invasive laser engraving. We already have ground-based laser systems powerful enough to focus a beam on a distant object. The breakthrough Starshot project, which Loeb chairs, is developing lasers designed to propel tiny spacecraft to Alpha Centauri by pushing them with focused light. Those same lasers could, in theory, be redirected to etch a message onto the surface of 3I/Atlas as it passes, a tattoo on the hull of an interstellar traveller. No physical contact required, just light, information, and hope that someone, somewhere, eventually reads it. The second option is more aggressive, the Barnacle probe. Launch a small, fast interceptor designed not to land gracefully, but to crash into the object and stick. Think of it like a harpoon, but at relativistic speeds. The probe would need to survive the impact, which at these velocities would be catastrophic for anything fragile. But if the payload is solid state, if it's just memory storage, radiation shielding, and a passive transmitter, it could work. It doesn't need to be smart. It just needs to be durable. The third option is the one that gets the least press but might be the most realistic, do nothing to 3I/Atlas itself. But catch one of the fragments. Remember, this object has been shedding material since it entered the inner solar system. Dust, ice, possibly larger chunks. Some of that material is still in orbit around the Sun. If we can identify a fragment, track its orbit, and send a mission to retrieve it, we'd have a sample of interstellar matter without needing to chase the parent object at all. Slower, safer, but we'd only be studying the debris, not sending anything outbound. Each of these plans has a countdown attached to it. 3I/Atlas is currently 200 million kilometers from Earth and accelerating away. The laser option has maybe 6 months before the object is too far for effective targeting. The Barnacle probe would need to launch within the next year to have any chance of intercept. And the fragment retrieval mission could take years to plan. But the fragments themselves are on decaying orbits. Some of them will fall into the Sun. Others will be ejected from the solar system entirely. The window is closing. Do you see the dilemma here? We have an opportunity that might not come again for decades, maybe centuries. An interstellar object, moving fast, on a known trajectory, still close enough to reach, but using it, catching it, or even just marking it, requires making decisions faster than scientific consensus usually moves. Committees take months. Funding approval takes years. And this object doesn't care about our bureaucracy. Loeb has been criticised for moving too fast, for proposing missions before the data is even fully analysed. But his counter-argument is simple. If we wait for certainty, we wait forever. And by the time we're certain what 3I/Atlas is, it'll be gone. So the question isn't just can we ride it? The question is, are we brave enough to try before we fully understand what we're riding? Because there's another layer to this that Loeb himself has acknowledged. And it's the part that makes some of his colleagues nervous. If this object is artificial, if it's a probe or a transport from another civilization, then attaching ourselves to it is making contact. Not passive observation, active engagement. We'd be saying, we see you and we're coming along, and what if whatever built this object doesn't want passengers? In science, the moment you get a precise measurement is often the moment everything stops making sense. For months, astronomers have been arguing about the size of 3I/Atlas. Early estimates ranged wildly, from a few hundred metres to several kilometres across. The uncertainty wasn't incompetence, it was physics. When you're looking at an object surrounded by a massive cloud of gas and dust, a coma that stretches millions of kilometres, you're not seeing the object itself, you're seeing the atmosphere it's dragging along. It's like trying to measure the size of a light bulb by looking at the glow on a foggy night. But last week, a team led by Dr. Kwanzi Ye at the University of Maryland published refined measurements using a different method. Instead of trying to see through the coma, they analysed how the object moves. Specifically, they looked at the non-gravitational acceleration we talked about earlier, the extra push that can't be explained by the sun's gravity alone, by measuring how much thrust that venting produces and comparing it to how much the object's trajectory changes. You can work backwards to estimate mass and size. Their conclusion, the nucleus, the solid core at the centre of all that gas and dust, is approximately 1 kilometre in diameter. 1 kilometre, that's small, smaller than most of the comets we track closely. Comet Hale-Bopp, the great comet of 1997 that was visible to your naked eye for months, had a nucleus about 60 kilometres across. Halley's comet is roughly 15 kilometres long. Even Comet 67P, the one the European Space Agency's Rosetta mission landed on, is about 4 kilometres wide. 3I/Atlas, if this measurement is correct, is a fraction of those sizes, and yet it's producing one of the most dramatic coma and tail structures we've seen from any recent comet. The tail stretches millions of kilometres. The coma glows intensely in telescopic images. It's behaving like something much, much larger. So here's the problem. Where is all that material coming from when a comet vents gas? It's losing mass, ice turns to vapour, dust gets blown away, and the nucleus gradually shrinks. This is normal. This is why comets have limited lifespans. After enough passes near the sun, they either break apart or become dormant, all their volatile material exhausted. A 1 kilometre comet can absolutely produce a visible coma and tail. But the rate at which 3I/Atlas is venting, the sheer volume of material it's releasing, doesn't match a body that small. Doctor. Ye's paper includes a troubling calculation. If the nucleus is truly 1 kilometre across and it's been venting at the observed rate since it entered the inner solar system back in August, it should have lost a significant percentage of its total mass by now. We're talking about structural stress levels that would cause fracturing, breakup, disintegration. Think of it like an ice cube in hot water. The smaller the cube, the faster it melts. And if you're generating steam, if you're boiling violently, that ice cube doesn't just melt, it shatters. The thermal shock, the pressure from expanding gas inside, it tears the structure apart. 3I/Atlas should be crumbling, but it's not. It's holding together. Dr. Matthew Knight, who's been tracking this object since discovery, went on record saying that if the size estimate is accurate, we're looking at an object with either extraordinary structural integrity or an internal composition unlike any comet we've studied before. Those are careful words, scientific words. But what they mean is simple. This doesn't add up. Let's compare this to a comet we know intimately. In 1994, you might remember Comet Shoemaker-Levy 9. That comet got too close to Jupiter, and tidal forces ripped it apart into more than 20 fragments before it crashed into the planet's atmosphere. The pieces weren't even that small. Some were estimated at 1 kilometre or more across. But the stress was too much. The comet broke. 3I/Atlas came within 11 million kilometres of the Sun. That's inside the orbit of Venus. The temperatures there exceed 400 degrees Celsius in some regions. The solar radiation is intense, and this object, supposedly a fragile ball of ice and rock just 1 kilometre wide, not only survived, it started venting harder after it left. There are two ways to explain this. The natural explanation requires the object to be made of something incredibly strong. Not just ice, but maybe a core of solid rock or metal, wrapped in a thin layer of volatiles. The venting we see would be surface activity only, the core remaining intact. Some comets do have rocky cores, we've seen that. But a core strong enough to survive this kind of thermal stress while the surface is actively boiling off? That's rare. Very rare. And here's where the numbers get uncomfortable. For a 1 kilometre object to maintain structural integrity under these conditions, the tensile strength, the ability of the material to hold together under stress, would need to be comparable to solid rock or even processed metal, natural ice, even compacted ice mixed with dust. It doesn't have that kind of strength. It fractures, it crumbles. So either 3I/Atlas is a 1 in a million natural object with just the right composition, just the right internal structure, and just the right rotation to have survived this journey without breaking apart. Or we're looking at something that was designed to survive it. Let's pause on that word designed. Not built by humans, obviously, but engineered, reinforced, a hull, not a rubble pile. If this object has internal support structures, if there's anything inside providing rigidity beyond natural compression, then a 1 kilometre sphere suddenly makes more sense. That's not a comet. That's a ship. A kilometre-wide ship, for context, is enormous by our standards. The International Space Station could fit inside it dozens of times over. The largest aircraft carrier ever built is about 340 metres long. 3 of them, end to end, wouldn't span this object's diameter. If 3I/Atlas is artificial, it's not a probe, it's a station, a arc. A generation ship built across the vast distances between stars. And the gas we're seeing, the massive tail, the venting that started after perihelion. If this is a machine, that's not sublimation, that's propulsion, that's course correction, that's an engine firing. But let's be fair to the natural explanation, because it's still on the table. There's a type of comet called a contact binary. 2 objects that merge together, creating a dumbbell or peanut shape. These shapes can be surprisingly strong because the mass is distributed in a way that resists tidal forces. If 3I/Atlas is a contact binary, if it's 2 smaller bodies stuck together, that could explain the structural integrity. The rotation would be more stable, the stress more evenly distributed. The problem is we don't have high-resolution images. We can't see the shape directly. We're inferring everything from light curves, from how the brightness changes over time, and those curves are frustratingly smooth. A contact binary usually shows a double-peak light curve as the 2 lobes alternately face us. 3I/Atlas doesn't show that. It's too steady, too uniform. So we're left with a paradox, an object too small to be doing what it's doing, too strong to be made of what comets are made of, and too stable to be tumbling naturally through space. Every measurement we take, every refinement of the data, seems to make it less likely that this is just a comet and more likely that we're looking at something else entirely. And if it's something else, if there's even a chance that the hull is artificial, then the question isn't just about size anymore. It's about contents. Because a 1 kilometre ship, if that's what this is, doesn't travel empty. There's a particular kind of fear that comes from knowing something toxic is floating above your head and not being entirely sure if it's going to fall. When astronomers first analysed the spectroscopic signature of 3I/Atlas, when they broke down the light coming from its coma into individual wavelengths to see what molecules were present, they found exactly what you'd expect from a comet water vapour, carbon dioxide, simple organic compounds, normal stuff, the building blocks of solar system chemistry, and then they found cyanide, specifically hydrogen cyanide, HCN, a molecule that, in sufficient concentrations, is lethal to pretty much every form of life we know. Your body can't process it. It binds to the enzymes that help your cells use oxygen, essentially suffocating you at the cellular level. A few hundred parts per million in the air you breathe, and you have minutes, maybe less. Before you start worrying about the air outside your window, let's be clear, finding cyanide in a comet is not unusual. Comets are ancient. They formed in the outer solar system where chemistry happens differently, where carbon and nitrogen combine in ways that don't happen on warm planets like Earth. Halley's comet has cyanide. Comet Hale-Bopp had it. It's part of the standard inventory of frozen materials that comets carry, but the concentration in Threa/Atlas caught attention. Dr. Martin Cordner at NASA's Goddard Space Flight Center, who led the spectroscopic analysis, noted that the HCN emission lines were stronger than expected for an object of this size. Not off the chart strong, but enough to warrant a second look. Enough to make you wonder if this object is venting harder than it should be. Is it also releasing more poison than it should be? And that led to a question that sounds almost paranoid until you think about it seriously. Could any of this material reach Earth? Avi Loeb addressed this directly in a technical note published on December 23rd, just 4 days after perihelion. The paper was titled, Diplomatically, Will Material from Threa/Atlas Arrive on Earth? And the short answer, the one that let a lot of people sleep easier, was probably not. Here's why. The solar wind, that constant stream of charged particles flowing outward from the sun, acts like a barrier. It pushes against the gas and dust streaming from the comet, sweeping it away from the inner solar system. The smaller the particle, the more easily it gets pushed. Loeb calculated that anything smaller than about 1 micrometer, about 1/100th the width of a human hair, gets deflected almost instantly. The solar wind is stronger than the comet's momentum for particles that tiny. They're blown outward, away from Earth, like leaves in a gale. Larger particles, gravel-sized chunks, a few millimeters across, have enough mass to resist the solar wind somewhat, but they're also sparse. The odds of one of those fragments happening to intersect Earth's orbital path, which is millions of kilometers wide, are astronomically small. We're talking lottery winner odds, except the prize is getting hit by a cosmic pebble travelling at 60 kilometers per second. So the physics, the natural mechanics of solar system dynamics, protect us. The comet's tail, the cyanide-laced gas cloud, the dust it's shedding, all of that material is being pushed outward and dispersed into space. It's not raining down on us. We're safe. Unless, and Loeb included this caveat in his paper, and it's the kind of caveat that makes you read the sentence twice. This assumes, of course, that the released objects cannot maneuver by technological propulsion. Let that sink in for a second. The safety calculation, the reason we're not worried about contamination, relies entirely on the assumption that the material is passive, that it's just dust and gas, governed by gravity and solar wind and nothing else. But if anything in that cloud, any of the fragments, any of the particles, has the ability to adjust its trajectory, to fire a tiny thruster, to navigate, then the solar wind doesn't matter, then the odds don't matter, then the fragments can go wherever they're programmed to go. We've seen this concept before, not from alien visitors, but from our own technology. In 2005, the Japanese spacecraft Hayabusa visited an asteroid called Itokawa and released a small probe called Minerva. The probe was designed to hop across the asteroid's surface using tiny bursts from a thruster. It missed the asteroid, unfortunately, a navigation error, but the concept was sound, a small, mobile object capable of adjusting its path in space. If Threa/Atlas is releasing anything similar, if the venting isn't purely natural but includes deployment of small guided objects, then spectroscopy alone won't tell us. We'd be looking at what appears to be dust, chemically identical to comet material, but behaviourally different, controllable. Now, let's talk about what happens if something does make it through, not cyanide gas that disperses too quickly to be a threat at these distances, but a physical object, a fragment, a capsule. There's a term in astrobiology directed panspermia, the idea that life, or the precursors to life, could be intentionally spread from one world to another, not by accident, not by random meteorite impacts, but by deliberate seeding. You send out probes carrying biological samples, organic compounds, maybe even dormant microorganisms, and you drop them into the atmospheres or oceans of planets that look promising. It's speculative, yes, but it's not impossible. We've even considered doing it ourselves. There are proposals, mostly theoretical, for sending microbes to Mars, to Europa, to Enceladus, to see if they can survive, to see if life from Earth can adapt to alien environments. We haven't done it, not yet, but the technology exists. The ethics are complicated, but the science is straightforward. What if 3I/Atlas is doing the reverse? What if the cyanide, the toxic chemistry, isn't a threat but a preservative cyanide? In the cold of space, is stable. It doesn't degrade, and certain extremophile organisms on Earth, bacteria that live in deep-sea vents, in volcanic springs, can tolerate or even metabolize cyanide-rich environments. If you wanted to send biological samples across interstellar distances, packaging them in a cyanide ice matrix might actually be a smart way to keep them viable. And here's where the timeline gets interesting. In the weeks following perihelion, there have been scattered reports from amateur astronomers and meteor tracking networks of unusual fireball activity. Not meteor showers, those are predictable, tied to specific comet debris streams we've mapped for decades. These are isolated events, single objects, bright orange or green in colour, moving slower than typical meteors. Normal meteors hit Earth's atmosphere at 20 to 70 kilometers per second and burn up in seconds, creating the brief streaks of light you see on a clear night. But several of the reported fireballs associated with 3I/Atlas, and this is based on trajectory analysis from camera networks in the US and Australia, were moving at closer to 12 to 15 kilometers per second, slower, and they lasted longer. Some were visible for 5 to 7 seconds before disappearing. That's consistent with objects that are decelerating, objects that are experiencing more drag than they should, possibly because they have a higher surface area relative to their mass, or because they're designed to slow down. Heat shields work by creating drag. They blunt the impact of atmospheric entry, spreading the heat over a larger area, allowing the object inside to survive. Do you see where this is going? If you wanted to deliver something to Earth's surface, you wouldn't send it in at full comet speed. You'd send it in a protective shell, something that can withstand re-entry, and you'd aim for a trajectory that maximizes drag and minimizes heat. You'd make it look like a meteor, bright and dramatic, something people would see and then forget because meteors happen all the time. The American Meteor Society logged 14 reports of unusual fireballs in the week following December 19th. 14 reports doesn't sound like much, but most meteors go unreported. Most burn up over oceans, over unpopulated areas, during daylight when no one's looking up. If 14 were seen, how many weren't NASA's Near-Earth Object Program hasn't issued any warnings? There's no official concern about impacts. And that makes sense if the objects are small, if they're burning up completely, leaving nothing but vapour and ash. But if even one of those fireballs made it to the surface intact, if there's a capsule sitting in a field somewhere, in a forest, at the bottom of a lake, then the question isn't whether 3I/Atlas dropped samples. The question is what's in them. Loeb's calculation protects us from passive debris. It doesn't protect us from targeted delivery. And the presence of cyanide in the coma, rather than being a red flag of danger, might actually be a signature of preservation. A chemical fingerprint that says this material was packaged for survival. Silence in space is never really silent. It's just noise you haven't learned to filter yet. On July 2nd, 25 months before 3I/Atlas made its closest approach to the Sun, the Allen Telescope Array in Northern California locked onto the object and listened. For 7 hours and 12 minutes, 42 radio dishes, each 6 meters wide, pointed at a patch of sky tracking this incoming visitor, scanning frequencies from 1 to 10 gigahertz, waiting for something that wasn't random, waiting for a pattern, a signal, proof. The Allen Array is part of the SETI Institute's ongoing search for extraterrestrial intelligence. It's designed specifically to detect artificial radio transmissions, the kind of structured signals that don't occur naturally. Think of it like the difference between static on an old TV and a broadcast. Static is random. A broadcast has rhythm, repetition, information encoded in the pattern. The array can distinguish between the two. And over those 7 hours, it detected 74 million signals. Now, before you get excited or terrified, depending on your disposition, that number is completely normal. The sky is full of radio noise, satellites, GPS systems, cell phone towers, microwave ovens, aircraft transponders, all of it radiating electromagnetic energy that bleeds into the frequencies astronomers are trying to monitor. When you point a radio telescope at anything, you're not just hearing the target, you're hearing everything between you and the target, and a lot of it is us. Humanity is loud, radioactively speaking. The job of the SETI team, led by Dr. Andrew Siemion at the Berkeley SETI Research Center, is to filter that noise. They have algorithms designed to identify and remove known sources. If a signal matches the frequency of a GPS satellite, it gets tagged and discarded. If it's coming from the wrong direction, if it doesn't track with the object's motion across the sky, it's background interference and gets filtered out. The process is meticulous, it's tedious, and it's necessary. After the filtering, after removing every signal they could confidently attribute to terrestrial or known satellite sources, they were left with 211 hits. 211 signals that came from the direction of 3I/Atlas that matched the object's movement, and that didn't fit any known pattern of interference. That sounds significant. That sounds like something. And for a few days, internally, before the data was made public, it probably felt like the biggest moment in SETI history. Then they analysed the waveforms. They looked at the structure of the signals, the frequency drift, the modulation patterns, and every single one of them, all 211, showed characteristics consistent with random noise or artifacts from the detection equipment itself. There was no repetition, no structure, no information content, just spikes in the data that happened to align with the object by coincidence. The official conclusion, published in the Astronomer's Telegram on July 18th, was no signals worthy of additional follow-up. In other words, we found nothing. 3I/Atlas is not broadcasting. But here's the part that doesn't sit right. The detail that keeps appearing in the footnotes of the analysis. The team calculated an upper limit on transmission power. If 3I/Atlas does have a transmitter, if it's sending out radio signals and we're just not detecting them, then the power of that transmitter must be below a certain threshold. Based on the sensitivity of the Allen array and the distance to the object at the time, they determined that any transmitter on 3I/Atlas would need to be operating at less than 10 to 110 watts to remain undetected. Think about that number for a second. 100 watts. That's a standard incandescent light bulb. That's a laptop charger. The radio transmitter in your cell phone, when it's operating at maximum power to reach a distant tower, uses about 2 to 3 watts. The transmitters on the Voyager spacecraft, the ones still sending data back to Earth from the edge of the solar system, operate at 23 watts. If 3I/Atlas is transmitting at 100 watts, it's whispering. It's not shouting a greeting to the solar system. It's using barely enough power to send a signal across interplanetary distances, and even that would require incredibly precise targeting. A 100-watt transmitter, directed at a specific receiver, using a focused beam rather than broadcasting in all directions, could absolutely communicate across millions of kilometres, but you'd never hear it unless you were the intended recipient. This is where the silence becomes suspicious rather than reassuring. Why would an interstellar probe use low power? 2 reasons: efficiency and stealth. Efficiency makes sense if you're trying to conserve energy. Interstellar journeys are long. If 3I/Atlas has been travelling for thousands or even millions of years, every watt of power matters. You don't waste energy broadcasting to empty space. You wait until you have data worth sending, and then you send it in short, efficient bursts to a relay or a receiver that you know is listening. Stealth makes sense if you don't want to be noticed. If you're a surveillance probe, if your job is to observe without interfering, you don't announce yourself. You collect data quietly. You transmit in narrow beams, encrypted, on frequencies that blend into the background noise. You make yourself look like nothing, like random static, so that the civilization you're studying doesn't realize they're being studied. Both scenarios fit the data. Both explain why we heard nothing, and both are deeply unsettling in different ways. Let's compare this to something we've done ourselves. The Hubble Space Telescope, when it transmits data back to Earth, uses a 2 GHz radio link operating at about 1 kilowatt of power. That's 10 times stronger than the upper limit calculated for 3I/Atlas. And Hubble is only transmitting across 550 kilometres. The distance between the telescope's orbit and the ground stations below. If 3I/Atlas is transmitting across millions of kilometres with 1/10 the power, it's either using incredibly advanced technology to focus the beam, or it's not trying to talk to us at all. And here's the other possibility, the one that makes the 211 anomalies worth a second thought. What if we were listening at the wrong time? The observation window was 7 hours. In cosmic terms, that's a blink. If 3I/Atlas transmits on a schedule, if it sends bursts of data every few days or every few weeks, synchronized with specific orbital positions or alignment with its home system, then a 7-hour window might have been too narrow. We might have been listening during a quiet period between transmissions, hearing the silence because there was genuinely nothing to hear at that moment. SETI researchers call this the temporal bias problem. We assume that if a signal exists, it's constant, always on, always detectable. But that's a very human assumption. Our own deep space network, the system NASA uses to communicate with distant spacecraft, only transmits during scheduled contact windows. The rest of the time, the spacecraft are silent, conserving power, executing their programming, waiting for the next check-in. If 3I/Atlas operates the same way, if it has a schedule, then we'd need to listen for weeks, maybe months, to catch a transmission. The July observation was a snapshot. It proved we can point our instruments at the object and record data. It didn't prove the object is silent. It proved we didn't hear anything during those specific 7 hours. So what would a real transmission look like? What would we need to detect to move beyond no signal to confirmed artificial source? SETI scientists look for a few key markers. First, a narrow bandwidth signal, natural sources, like pulsars or radiation from gas clouds, emit across a wide range of frequencies. Artificial transmitters focus energy into a narrow band to maximize signal strength. Second, frequency drift that matches the object's motion. If the signal is Doppler shifted in a way that corresponds to the object's velocity relative to Earth, that's strong evidence it's coming from the object and not from background noise. Third, modulation patterns. Information is encoded by varying the signal, amplitude modulation, frequency modulation, patterns that repeat, structures that can't happen by accident. None of the 211 anomalies showed these characteristics. But absence of evidence, as the saying goes, is not evidence of absence. It just means we need better tools, longer observation windows, or a different approach entirely. And that brings us back to the power calculation. If 3I/Atlas is transmitting at 100 watts or less, and if it's using a directional antenna, a beam aimed not at Earth but at a specific point in space, then we wouldn't hear it at all, unless we were in the path of that beam. And where is that beam pointed? The answer might depend on where the object is going next, because in less than 3 months, 3I/Atlas will pass within 53 million kilometres of Jupiter, close enough that the giant planet's magnetosphere, one of the most powerful magnetic fields in the solar system, could act as a natural amplifier. If you wanted to send a message, if you had data to upload, Jupiter would be the perfect relay station. There are places in the solar system where physics gets amplified, where the rules we're used to on Earth bend into something more extreme, more powerful. Jupiter is one of those places. March 16th, 2026. That's the date 3I/Atlas will pass within 53 million kilometres of the largest planet in our solar system. To put that in perspective, that's about 1/3 the distance between Earth and the Sun. In cosmic terms, that's close. Close enough that Jupiter's gravitational influence will tug on the object's trajectory. Close enough that the radiation environment, the charged particles trapped in Jupiter's magnetic field, will be intense. And close enough that if this object has any communication equipment, any transmitter waiting for the right moment, this would be it. Because Jupiter isn't just a planet, it's infrastructure. Let's talk about what makes Jupiter special from a communication standpoint. The planet has a magnetic field that extends millions of kilometres into space, roughly 20,000 times stronger than Earth's. That magnetosphere, the bubble of magnetic influence surrounding the planet, traps charged particles from the solar wind and creates what's essentially a massive natural antenna. Radio waves that pass through or interact with this field can be amplified, redirected, broadcast across distances that would normally require far more power. We've known about this since the 1950s, when radio astronomers first detected powerful bursts of radio emission coming from Jupiter. These weren't signals from the planet itself, but rather the result of interactions between Jupiter's magnetic field and its moon Io, which constantly spews volcanic material into space. That material gets ionized, charged, and when it spirals along Jupiter's magnetic field lines, it creates radio bursts so strong we can detect them with backyard equipment here on Earth. If you wanted to send a message across interstellar distances and you had limited power, you wouldn't just broadcast from empty space. You'd wait until you were near a natural amplifier. You'd use Jupiter as a relay. Dr. Imke Depata, a planetary scientist at UC Berkeley who has spent decades studying Jupiter's magnetosphere, has noted that any spacecraft passing through that environment would experience radio interference patterns that could either scramble a signal or, if designed correctly, boost it significantly. NASA's Juno mission, currently orbiting Jupiter, has to account for this. The spacecraft's communication system is built to handle the noise, to filter out the background static created by the planet's intense magnetic activity. But what if you didn't want to filter it out? What if you wanted to use it? There's a concept in radio engineering called ionospheric reflection. On Earth, radio operators use the ionosphere, the layer of charged particles in our upper atmosphere, to bounce signals beyond the horizon, to communicate across continents without satellites. The signal hits the ionosphere, reflects back down, and reaches a receiver thousands of kilometres away. Jupiter's magnetosphere could work the same way, but on a vastly larger scale. If 3I/Atlas has a transmitter, and if that transmitter activates during the Jupiter flyby, the signal could interact with the planet's magnetic field in ways that amplify its reach. A 100-watt signal, the upper limit we calculated earlier, could potentially be boosted to the equivalent of several kilowatts by the time it exits Jupiter's magnetosphere. That's enough power to be detectable across light years, not just across the solar system, and the timing matters. The object will reach its closest approach to Jupiter at approximately 1437 UTC on March 16th. At that moment, the alignment between 3I/Atlas, Jupiter, and certain distant stars will be precise. If the object is trying to send data back to Epsilon Eridani, its suspected origin 146 light-years away. This alignment would provide the clearest path, the least interference. Now, You might be wondering if Jupiter is such a good relay. Why don't we use it ourselves? Why aren't we parking satellites near Jupiter to boost our own interstellar messages? We've thought about it. In fact, there's a proposal from the Breakthrough Message Initiative, the same group involved in designing messages to send to other star systems, to use gravitational slingshots around Jupiter to send probes outbound with encoded information. The problem is energy. Getting to Jupiter requires a lot of fuel or a very long, slow trajectory using multiple planetary flybys. And even if you reach Jupiter, you still need a transmitter powerful enough to make the signal worthwhile. It's theoretically efficient, but practically difficult, unless you're already passing by anyway, unless your trajectory naturally takes you past the relay point, and all you need to do is turn on the transmitter at the right moment. That's what makes the March 16th encounter so critical. If 3I/Atlas is a probe, if it has gathered data during its pass through the inner solar system, collected samples, recorded observations, taken measurements of Earth's atmosphere, our radio emissions, our technological signatures, then Jupiter is where it uploads that data. And once it uploads, once the signal is amplified and broadcast, it's out there. It's travelling at the speed of light toward whatever receiver is listening, and we can't stop it. Let's look at a historical precedent. In July 1994, comet Shoemaker Levy 9 collided with Jupiter in a series of impacts that were visible from Earth. Astronomers around the world watched as fragment after fragment slammed into the planet's atmosphere, creating fireballs larger than Earth itself. The impacts released energy equivalent to millions of nuclear weapons, and the radio emissions from those impacts, the bursts of energy detected by radio telescopes, were among the strongest non-solar signals ever recorded in our solar system. 3I/Atlas isn't going to collide with Jupiter. Its trajectory will keep it safely distant. But if it does transmit, if it uses the magnetosphere as a booster, the signal could be just as detectable, just as unmistakable, as those impact bursts were in 1994, and this time we'd know it wasn't natural. This time we'd be listening specifically for it. NASA's Deep Space Network, the global array of radio antennas used to communicate with distant spacecraft, has already been scheduling observation time around the March 16th window. Officially, the purpose is to monitor the object's trajectory, to refine orbital predictions, to gather additional spectroscopic data. But reading between the lines, looking at the allocated resources, the DSN is preparing for something more than passive observation. They're preparing to listen. The European Space Agency's ExoMars Trace Gas Orbiter, currently in orbit around Mars, has also been repositioned to have a line of sight to both 3I/Atlas and Jupiter during the encounter. The orbiter's instruments are designed to detect faint atmospheric signals, trace gases, exactly the kind of sensitive equipment that could pick up unexpected radio emissions. ESA hasn't issued a press release about this. It's mentioned in internal scheduling documents, the kind of technical updates that only mission planners read. But it's there. So the world's space agencies are watching. They're listening. And they're not telling the public exactly what they're expecting to find, or what they're afraid they might hear. Here's the uncomfortable part. If the signal goes out, if 3I/Atlas transmits and we detect it, what do we do? Do we respond? Do we try to jam it? Do we attempt to intercept the object before it reaches Jupiter, before it has the chance to use the relay? Because there's another layer to this, a strategic consideration that hasn't been widely discussed outside of classified briefings. If 3I/Atlas is sending data about Earth, about our defences, our technology, our biology, back to its origin point, then allowing that transmission to complete is a potential security risk, not an immediate one. The signal would take 146 years to reach Epsilon Eridani, and any response would take another 146 years to return. We're talking about timescales longer than nations, longer than governments. But strategically, letting an unknown intelligence gather detailed information about your civilization and then successfully report back is, at minimum, worth debating. And that debate is happening, just not in public. There are proposals circulating in aerospace defense circles to use the Jupiter encounter as an opportunity for what's being carefully termed trajectory modification. The idea is to launch a kinetic impactor, essentially a very fast projectile, to intercept 3I/Atlas before March 16th, not to destroy it necessarily, but to alter its path, to push it off course so that it misses the optimal alignment with Jupiter. If the object can't use the magnetosphere as a relay, if it's forced to transmit from a less favourable position, the signal strength drops dramatically. It becomes harder to detect, harder to decode, easier to lose in the noise of interstellar space. The mission would be framed as scientific curiosity. We're nudging the object to study its composition, to see how it reacts to an impact, to gather data on its structural integrity, but the real purpose would be sabotage. Quiet, deniable, and potentially justified if you believe the object poses a long-term threat. But here's the risk. What if interfering triggers a response? What if the object has fail-safes? Protocols designed to react to hostile action, we're assuming it's passive, that it's just collecting and transmitting, but if it's capable of defense, if there are systems on board that activate when threatened, then poking it might be the worst decision humanity could make. When you watch a comet pass through the inner solar system, you're not just watching one object, you're watching a cloud, a stream, a trail of debris that stretches millions of kilometres behind the main nucleus. Most of that material is temporary, ice particles and dust that will either evaporate in the sunlight or drift into stable orbits that eventually decay. But some of it stays. Some of it becomes permanent residents of our solar system. And with 3I/Atlas, we have no idea how much stayed behind. Dr. Quanzi Ye, the same astronomer who calculated the 1 kilometre nucleus size, has been tracking something else, the orbital evolution of fragments. Not the main object, but the smaller pieces, the material that separated from 3I/Atlas during its months-long journey through the inner solar system. His preliminary models, published in a preprint paper on December 28th, suggest that between 15 and 30 distinct fragments, ranging from a few centimetres to possibly a few metres across, are now in independent orbits around the Sun. Most of them are following trajectories similar to the parent object, outbound, leaving the solar system at high speed, but 3, possibly 4, of the tracked fragments show orbital characteristics that suggest they've been captured. They're not leaving, they're staying here, locked into elliptical paths that will bring them back to the inner solar system repeatedly over the coming decades. Think about what that means. We now have interstellar material, objects that originated outside our solar system, in permanent orbits around our Sun. They'll be here long after 3I/Atlas has disappeared into the dark, and we don't know what they are. The fragments are too small to observe directly with most telescopes. We're not talking about objects you can photograph and analyse in detail. We're talking about faint points of light that occasionally reflect sunlight, that show up in tracking data as brief flashes, trajectory calculations based on probability more than certainty. But the fact that they exist, that they separated from the main object and survived independently, tells us something important. They're durable. Natural comet fragments tend to be fragile. When a comet sheds material, it's usually because thermal stresses cause cracks, because the ice has sublimated unevenly and chunks have broken off. Those chunks are structurally weak. They often break apart further, disintegrating into dust over the course of weeks or months. The fact that these fragments from 3I/Atlas are maintaining cohesion, that they're still trackable objects rather than dispersed clouds, suggests they're either unusually dense or they have some kind of internal structure that's holding them together. Now let's talk about the fireball reports, because this is where the data gets genuinely strange. The American Meteor Society, a volunteer organisation that collects reports of meteor sightings from observers around the world, logged 47 fireball reports between December 19th and December 31st that are classified as potentially associated with Interstellar Object 3, WOB/Atlas. That classification is based on trajectory analysis, comparing the reported direction and speed of the fireball with the predicted debris field from the comet. 47 reports in 12 days. That's higher than baseline, higher than what you'd expect from random meteor activity during that time of year. But here's what makes it interesting. 11 of those 47 reports describe fireballs that were orange or amber in colour, rather than the typical white or blue-green you see from meteors burning up in the atmosphere. Colour tells you about composition. White fireballs are usually stony material, rock and silicates burning at high temperature. Blue-green indicates magnesium or copper, metals vaporizing. Orange suggests a different chemistry, possibly organic compounds, carbon-rich material, or in some cases, iron oxide, rust. If you were designing a heat shield for atmospheric entry, if you wanted something that could survive the intense heat and friction of plunging through Earth's atmosphere at high speed, you'd coat it in ablative material, something that burns away gradually, dissipating heat. And many ablative materials, when they burn, produce an orange glow. Is that what we're seeing? Heat shields burning off as interstellar capsules decelerate through the atmosphere? Dr. Peter Jenniskens at the SETI Institute, who specialises in meteor spectroscopy, analysed 3 of the reported orange fireballs using camera network data from NASA's All-Sky Fireball Network. His findings, shared in an internal memo that was later leaked to online astronomy forums, indicate that at least one of the fireballs showed a deceleration profile inconsistent with typical meteor behaviour. Normal meteors decelerate predictably. They hit the atmosphere, the drag increases, the object slows down and burns up, usually within 2 to 5 seconds. The deceleration curve follows a smooth mathematical pattern. But one of the orange fireballs tracked by Jenniskens showed a stepwise deceleration, a pattern where the object slowed down in stages rather than continuously. That's consistent with controlled entry, with a heat shield that's shedding layers, reducing the object's mass in a way that stabilizes the descent. The fireball lasted 9 seconds. It was visible from Northern California to Southern Oregon, and it didn't burn up completely. The terminal point of the trajectory, the place where cameras lost track of it, was at an altitude of approximately 17 kilometres. Most meteors are gone by 30 kilometres. If this object made it down to 17 kilometres and was still intact, still glowing, then it might have reached the surface. Jenniskens filed a request with the USES, Geological Survey, to check seismic data for impacts in the predicted landing zone, a remote area of the Cascade Range in Northern California. The USGS response, dated January 4th, states, "No seismic events consistent with meteorite impact detected in the specified region during the time window," which means either the object was too small to register on seismic sensors, or it landed in a way that didn't create a shockwave. Soft landing, controlled landing. Do you see the problem here? We're operating on incomplete data, on assumptions that might not hold if the objects are artificial. We assume meteors burn up. We assume fragments disintegrate. We assume that anything falling from space is passive, governed by physics alone. But if even one of these fragments is guided, if it has thrusters or aerodynamic surfaces or any ability to control its descent, then our assumptions are wrong. And there's another complication: GPS anomalies. Between December 20th and January 8th, there were 23 reported incidents of localized GPS disruption in regions across North America, Europe, and Australia. These weren't widespread blackouts, not the kind of interference you'd see from solar flares or military jamming. These were small-scale, temporary glitches lasting between 30 seconds and 4 minutes, affecting areas roughly 10 to 20 kilometers in diameter. The official explanation from GPS service providers is ionospheric disturbances, pockets of charged particles in the upper atmosphere that can temporarily block satellite signals. That's plausible. It happens occasionally, especially during periods of heightened solar activity. But the sun has been relatively quiet recently. Solar activity is in a low phase of the 11-year cycle, and the GPS disruptions don't correlate with solar events. They correlate with fireball reports. Dr. Todd Pedersen, a space physicist at the Air Force Research Laboratory, noted in a conference presentation that 8 of the 23 GPS anomalies occurred within 12 hours and within 500 kilometres of a reported orange fireball sighting. That's a statistical correlation worth investigating. It could be coincidence. Fireballs do create ionization trails as they burn through the atmosphere, and those trails can temporarily interfere with radio signals. But typically, that interference lasts seconds, not minutes. What if the fragments aren't just falling? What if they're transmitting a small transmitter, even a low-power one? Could cause localized GPS interference if it's broadcasting on frequencies close to the GPS bands. And if the fragments are equipped with transmitters, if they're designed to send a signal once they've landed, or once they've reached a certain altitude, that would explain both the GPS glitches and the lack of seismic impacts. They're not crashing, they're landing. And once they land, they're calling home. Now. This is speculative. There's no direct evidence of transmitters. There's no recovered fragment that we can examine and say, yes, this is artificial, but the pattern is there. Fireballs that don't behave like normal meteors, GPS disruptions that align with those fireballs, and fragments in stable orbits that suggest intentional deployment rather than random shedding. If you were sending a probe to study another star system, you wouldn't just fly through and leave. You'd drop sensors, you'd deploy instruments, you'd leave behind pieces that could continue gathering data long after the main probe had moved on. Earth-orbiting satellites do this. We deploy CubeSats from the International Space Station all the time. Small secondary payloads that separate and operate independently. Why wouldn't an interstellar probe do the same? The fragments could be autonomous data collectors, each one designed to monitor a different aspect of our planet. Atmospheric composition, electromagnetic emissions, biological signatures. And if they're transmitting that data back to the main object, or directly to wherever 3I/Atlas is headed, then the pickup mission isn't just about what the main object collected, it's about what the fragments are still collecting right now. And here's the unsettling part, we don't know where all of them are. We've tracked some, we've estimated orbits for a few. But the smaller fragments, the ones too faint to show up consistently in telescopic surveys, could be anywhere. In orbit, in the atmosphere, on the ground, waiting. There's a moment in every first contact scenario, real or imagined, where the scientists and the strategists stop agreeing on what should happen next. We've reached that moment. In early January, a proposal quietly circulated among aerospace contractors and defence research labs in the United States, Europe and Japan. The document, later referenced in a Defence News article on January 9th, outlined a mission architecture for what it called rapid intercept and characterization of near-solar interstellar objects. The language was careful, technical, sanitized, but the engineering specifications told a different story. The proposal wasn't for a science mission. It was for a weapon. At the core of the design is a kinetic impactor, essentially a guided projectile designed to collide with a target at extremely high velocity. We've built these before. NASA's DART mission, which successfully impacted the asteroid Dimorphos in September 2022, proved that we can hit a moving target in space with precision. DART was a test of planetary defense, a demonstration that if we ever detect an asteroid on a collision course with Earth, we have the technology to deflect it. But the proposal for 3I/Atlas isn't about deflection. It's about disruption. The mission profile calls for a launch window in late January or early February, giving the impactor enough time to reach 3I/Atlas before its March 16th approach to Jupiter. The spacecraft would be small, fast, and simple. No complex instruments, no sample return capability, just a guidance system, a propulsion module, and a solid mass designed to hit the object at a relative velocity of approximately 25 kilometers per second. At that speed, the kinetic energy of the impact would be equivalent to several tons of TNT. Not enough to vaporize a 1 kilometer object, not even close, but enough to fracture it, to break off pieces, to disrupt its structural integrity, and more importantly, enough to alter its trajectory by a small but measurable amount. Why would you want to do that? Why spend the resources to launch a mission designed to damage an object that's already leaving the solar system? The publicly stated rationale, the one you'd find in budget justification documents, is scientific. By impacting the object and analysing the debris cloud, the composition of the ejected material, we could learn what it's made of. We could answer definitively whether it's ice and rock or something else. The impact would force the object to reveal its interior, to show us what's beneath the surface. But the real reason, the one that doesn't appear in press releases, is strategic. If 3i/Atlas is going to use Jupiter as a relay, if it's planning to transmit data during the flyby, then altering its trajectory could ruin the alignment. The object would miss the optimal position. The magnetosphere boost wouldn't work as effectively. The signal, if there is one, would be weaker, harder to detect, easier to lose in the background noise of space. You're not destroying the messenger. You're just making sure the message doesn't get through. Dr. Linley Johnson, NASA's planetary defense officer until his retirement in 2022, has been outspoken about this approach. In an interview with Space News on January 12th, he argued that any kinetic impact mission targeting an interstellar object sets a dangerous precedent. His exact words, "We are making a choice as a species to interfere with something we don't understand. And we're doing it not because it threatens us directly, but because we're afraid of what it might tell someone else about us." That's the ethical dilemma at the heart of this. If the object is natural, if it's just a comet that happens to be behaving strangely, then hitting it is a waste of resources and a lost opportunity for science. But if the object is artificial, if it is gathering intelligence, then the question becomes, do we have the right to stop it? And more pressingly, do we have the responsibility to try? Let's look at the counter-argument, the one being made in classified briefings and defense journals. If 3i/Atlas is a probe from another civilization, then it has already observed us. It has already collected data, radio emissions, heat signatures, the spectroscopic fingerprint of our atmosphere, laced with industrial pollutants and the chemical traces of 7 billion humans. If that data gets transmitted back to its origin, if whoever sent this probe learns where we are and what we're capable of, then we've lost the one advantage isolation provides: anonymity. The universe is vast. Even our nearest stellar neighbours are light years away. The odds of another civilization stumbling across us by accident are vanishingly small. But if we're actively transmitting, if our location is being reported back by a probe we allowed to operate freely, then we've made ourselves visible. We've put a pin on the galactic map, and what happens after that is anyone's guess. There's a concept in military strategy called escalation control. The idea that in any conflict, you want to be the one who decides when and how things intensify. Letting 3i/Atlas reach Jupiter and transmit, if that's what it's planning to do, means we've given up control. We're passengers in a scenario we don't fully understand, waiting to see if anyone responds to the signal. And if they do respond, if there is a reply 146 years from now when the signal reaches Epsilon Eridani, we'll be long gone. But our descendants won't be. They'll be the ones dealing with the consequences of our decision. So the argument for intervention, for striking the object before March 16th, isn't about aggression. It's about buying time. It's about making sure that if contact happens, it happens on our terms, when we're ready, when we've had time to think it through. But there's another risk that the intervention advocates tend to downplay: retaliation. If 3i/Atlas has any autonomous defensive systems, if it's capable of detecting a threat and responding, then an impact could trigger exactly the kind of escalation they're trying to avoid. The fragments we talked about earlier, the ones in orbit around the sun, the ones possibly already in our atmosphere. What if they're not just passive sensors? What if they're contingency measures, sleeper systems designed to activate if the main probe is attacked? We've built similar systems ourselves. Military satellites often have self-defense capabilities, electronic countermeasures. ways to protect themselves or retaliate against interference. If we've thought of it, why wouldn't another intelligence doctor, Seth Shostak, senior astronomer at the SETI Institute, address this concern in a public forum at the American Astronomical Society meeting on January 6th? He pointed out that any civilization capable of sending a probe across interstellar distances is, by definition, more technologically advanced than we are. And attacking their technology, even in the name of self-defense, might be interpreted as hostility. His closing remark, half joking but entirely serious: "You don't slap the hand reaching out to you unless you're very sure it's not attached to something much larger. The problem is, we're not sure. We're not sure of anything. And in the absence of certainty, different groups are drawing different conclusions. The scientific community, broadly speaking, wants to observe. Keep watching. Keep listening. Gather more data before making irreversible decisions. Launch more telescopes. Point the James Webb Space Telescope at the object. Get spectroscopy detailed enough to see individual molecular structures. Patience and precision. The defense community wants to act. The window is closing. March 16th is less than 3 months away. And if we're going to do something, we need to decide now. Launch the impactor, disrupt the trajectory, prevent the transmission. Better to be cautious than caught off guard. And somewhere in the middle, there are the people who think we should try to communicate. Not with weapons, not with silence, but with a message of our own. Use the same laser systems Avi Loeb proposed for engraving, but instead of a passive tattoo, send a structured signal. Binary code. Mathematical constants. Something that says we see you, we understand what you are, and we're choosing to engage peacefully. 3 approaches, 3 philosophies, and only one of them can win, because the actions are mutually exclusive. You can't study something you've just hit with a kinetic impactor. You can't communicate with something you're trying to knock off course. And you can't do nothing if you believe the object poses a threat. So which path gets chosen who decides in theory? It would be an international decision, coordinated through the United Nations Office for Outer Space Affairs, the body responsible for managing humanity's activities beyond Earth. In practice, the countries with the rockets and the budgets will decide, and everyone else will find out after the fact. And if history is any guide, they'll choose the option that feels like control, even if it's an illusion. They'll choose the strike, not because it's the smartest move, but because doing something, anything, feels better than waiting and wondering. In detective work, motive often becomes clear when you understand the destination. When astronomers first calculated 3 I/Atlas's trajectory, when they traced its path backward through space, they found something unusual. The object didn't come from just anywhere in the galaxy. It came from a specific direction, from a region of sky that contains a star system we've been watching closely for decades, Epsilon Eridani. Epsilon Eridani is not a random point of light. It's one of the closest single stars to our Sun, sitting just 10.5 light-years away in the constellation Eridanus. That's practically next door in cosmic terms. Close enough that if you went outside on a clear night, found the constellation, you could see it with your naked eye, a faint orange point glowing at magnitude 3.7. But what makes Epsilon Eridani interesting isn't its proximity. It's what we know surrounds it. The star is younger than our Sun, roughly 400 to 800 million years old, still in what astronomers call the active phase of stellar evolution. It rotates faster, it's more variable, and it's surrounded by not 1 but 2 debris disks, vast rings of dust and rock left over from planet formation. We've confirmed at least 1 planet in the system, Epsilon Eridani b, a gas giant roughly the mass of Jupiter orbiting at about the same distance as Jupiter orbits our Sun. And there's evidence, still debated but growing stronger, of additional planets in the inner system, smaller worlds, possibly rocky, possibly in the habitable zone where liquid water could exist on the surface. Dr. Deborah Fisher, an exoplanet researcher at Yale University, has been studying Epsilon Eridani for over 20 years. Her team uses radial velocity measurements, tracking the tiny wobbles in the star's motion caused by orbiting planets tugging on it gravitationally. In a 2018 paper, she noted that the data suggests additional planetary mass companions in the system, though the signals are difficult to confirm due to the star's inherent variability. Translation, there might be Earth-like planets there. We just can't see them clearly yet. Now, here's where the trajectory analysis of 3a/Atlas becomes compelling when you run the object's orbit backward, accounting for gravitational interactions with the Sun and Jupiter, accounting for the non-gravitational acceleration we've observed, the most likely origin point. The region of space the object came from aligns almost perfectly with Epsilon Eridani's current position. Not where the star is now, but where it was roughly 10,000 years ago, accounting for the star's own motion through the galaxy and the time it would take an object travelling at 60 kilometres per second to cover 10.5 light years. The math works. The alignment is too precise to be coincidence. But let's be careful here. Trajectory analysis isn't proof of origin. Space is three-dimensional, and the further back you trace an orbit, the more uncertainty compounds. The object could have come from anywhere along that general direction. Epsilon Eridani just happens to be the most notable star in that region. The one with confirmed planets. The one we've been watching. Still, the possibility is enough to make you think. If 3i/Atlas did come from Epsilon Eridani, if it was sent by something living in that system, then this isn't a random exploration. It's targeted. Someone over there knows we're over here, and they sent something to check us out. Let's talk about timescales, because they matter. If the object left Epsilon Eridani 10,000 years ago, that puts the launch date somewhere around 8000 BCE by our calendar. That's the Neolithic period on Earth. Humans were just beginning to develop agriculture. The first cities were still thousands of years away. We weren't broadcasting radio signals. We weren't launching rockets from space. Earth would have looked like a quiet, blue-green world with no obvious signs of technology. So why send a probe here? What would have attracted their attention? One possibility: biosignatures. Even 10,000 years ago, Earth's atmosphere had oxygen, lots of it, produced by photosynthetic life over billions of years. Oxygen is reactive. It doesn't stay in an atmosphere unless something is continuously producing it. If you're scanning star systems for signs of life, looking at the spectroscopic signatures of distant planets, an oxygen-rich atmosphere is a massive red flag. It says something alive is here. If a civilization in the Epsilon Eridani system detected our biosphere, if they built telescopes powerful enough to analyse Earth's atmospheric composition from 10.5 light years away, they would have seen life. Not intelligent life. Not yet. But life. And that might have been enough reason to send a probe. Another possibility, more unsettling, they weren't looking for life. They were looking for resources. Epsilon Eridani is a young star, still surrounded by the debris of planet formation. But young systems are also chaotic. Planets are still migrating. Asteroids are still colliding, and the habitable zones might not be stable yet. If you're a civilization trying to survive in a turbulent system, you might look outward toward older, more stable stars to find what you need. Earth, from their perspective, is a mature planet orbiting a stable star. It has water, organic chemistry, a protective magnetic field, everything a thriving biosphere needs. If you're planning long-term, if you're thinking in terms of thousands or millions of years, you might send scouts to catalogue potential resources, not to invade immediately, but to mark the location, to gather data, to know what's available when you eventually need it. The probe doesn't need to return physically. It just needs to send a message, a data packet, coordinates, atmospheric composition, confirmation that the target system is viable. And then it moves on, or it stays, waiting, monitoring, reporting back periodically. Does this sound like science fiction, maybe? But it's also basic strategic planning. We've thought about doing the same thing. The Breakthrough Starshot Initiative, the same project Avi Loeb chairs, is designed to send tiny probes to Alpha Centauri at a significant fraction of the speed of light. Those probes would gather data and transmit it back. They wouldn't return. They'd be one-way scouts, verifying what our telescopes suspect, that there are planets in the Alpha Centauri system, possibly habitable ones. If we're thinking about sending scouts, why wouldn't someone else now? Let's consider the return trajectory. If 3I/Atlas successfully transmits its data at the Jupiter encounter, and if that transmission is directed back toward Epsilon Eridani, the signal would take 10.5 years to arrive, not 10,000 years, not centuries, just a decade. That's within a human lifetime, within the operational lifespan of our current technologies, which means if there's anyone listening on the other end, if there's a receiver in the Epsilon Eridani system designed to pick up this probe's reports, they could get the message before 2037, and if they respond, if they send a reply using the same communication method, we'd receive it by 2048. That's 23 years from now. Some of you reading this will still be alive. You might be the generation that hears the reply. But what would that reply say? Would it be a greeting, a confirmation of peaceful intent, an invitation to communicate further, or would it be instructions, coordinates, a signal to the fragments already here, activating them, telling them what to do next? Dr. Jill Tarter, former director of the SETI Institute, has spent her career thinking about these scenarios. In a 2019 lecture at the International Astronautical Congress, she addressed the question of what happens if we detect an intelligent signal and it's not just information, but a command structure, a set of instructions for something already in our solar system. Her conclusion: we need protocols, we need international agreements, because if the message is activate, we need to decide very quickly whether we're going to listen or whether we're going to jam the signal. We don't have those protocols. We don't have those agreements. And we're running out of time to create them. There's one more layer to this, something that most analyses overlook. Epsilon Eridani is part of a larger structure called the Ursa Major Moving Group, a collection of stars that form together and are still travelling through the galaxy in roughly the same direction. This group includes at least 60 confirmed stars, many of them similar to our Sun, many of them potentially hosting planets. If one civilization in that group developed interstellar travel, even slow, probe-based travel, they wouldn't just explore randomly. They'd map the neighbourhood. They'd send probes to every promising system within reach, building a network, a web of scouts reporting back, sharing data. 3I/Atlas might not be unique. It might be one of dozens, hundreds, scattered across nearby star systems, all part of the same exploration program, all launched millennia ago, all now converging on their targets and preparing to report home. And if that's true, if we're not dealing with a single anomaly but with a systematic survey, then Earth isn't special. We're just next on the list. One more data point in a galactic catalogue, one more world to be measured, assessed, and filed away for future reference. The question is, what happens when the filing is done? There's a concept in ecology called an indicator species, an organism whose presence tells you something important about the environment. When you find certain types of lichen on trees, you know the air quality is good. When you see specific fish in a river, you know the water is clean. The organism itself might be unremarkable, but what it indicates, what its existence implies about the larger system, that's what matters. 3I/Atlas might be our indicator species for something much larger. Let's step back and look at the bigger picture. The one that emerges when you stop focusing on this single object and start thinking about patterns. In the past 8 years, we've confirmed 3 interstellar objects passing through our solar system. Oumuamua in 2017, Comet 2I/Borisov in 2019, and now 3I/Atlas in 2025. 3 objects in 8 years. That might not sound like many, but consider what that detection rate implies. Our telescopes only see a tiny fraction of what's actually out there. We catch the objects that happen to pass close to Earth, that happen to be bright enough to detect. that happen to be discovered by sky surveys that are already overloaded tracking asteroids and other solar system bodies. For every interstellar object we detect, there are probably dozens, maybe hundreds, that we miss. They're too small, too dark, or their trajectories take them through parts of the solar system we're not monitoring closely. Dr. Avi Loeb, in a statistical paper published in 2021, estimated that at any given time, there could be 10,000 interstellar objects within the orbit of Neptune. Most of them dormant, most of them undetectable with current technology, but there, always there, passing through. If that estimate is even close to accurate, then the solar system isn't an isolated island. It's a highway interchange. Objects from other star systems are constantly moving through, crossing paths, some fast, some slow, some on their way out, others on their way in. We're not alone in an empty void. We're sitting in the middle of traffic we've only just started to notice. And if some of that traffic is artificial, if even a small percentage of those 10,000 objects are probes rather than natural debris, then we're not looking at a single visitor, we're looking at a network. The network hypothesis goes like this. Advanced civilizations don't explore the galaxy by sending crewed ships on century-long journeys. That's inefficient, dangerous, and unnecessary. Instead, they send probes. Lots of them. Small, durable, autonomous machines designed to travel for thousands of years, entering star systems, gathering data, and either transmitting back or waiting for retrieval. You don't need faster-than-light travel. You don't need generational ships. You just need patience and mass production. Launch 1,000 probes in every direction. Wait, over millennia, they reach neighbouring star systems, and the data starts flowing back. You build a map, a catalogue, a network of information about what's out there. We've thought about doing this ourselves. The concept is called a von Neumann probe, named after mathematician John von Neumann, who theorised about self-replicating machines. The idea is that you send out a probe, and when it reaches a star system with resources, it builds copies of itself using local materials. Those copies continue outward, reaching more systems, building more copies, exponential growth. Within a few million years, a relatively short time cosmically, the entire galaxy could be surveyed. The math works, the physics works. The only question is whether anyone has actually done it. If they have, if there's a network of probes moving through the galaxy, reporting back to their creators, then 3I/Atlas isn't an anomaly. It's part of standard operations, and Earth isn't being singled out. We're just one more system being catalogued. One more pin on a map that's been expanding for longer than our species has existed. That sounds almost comforting, doesn't it? We're not special. We're not being targeted. We're just data. But there's a darker edge to this scenario, one that researchers in astrobiology and planetary defence have been quietly discussing for years. If the network exists, if probes are routinely surveying habitable worlds, then the civilizations running that network have access to an enormous amount of information. They know which systems have life. They know which ones have technology. They know which worlds have resources worth extracting and which ones have inhabitants that might resist. Dr. Jacob Hack-Misra, an astrobiologist at the Blue Marble Space Institute of Science, co-authored a paper in 2013 exploring this scenario. The paper, titled The Sustainability Solution to the Fermi Paradox, suggests that advanced civilizations might practice what he calls selective expansion. They don't colonize every habitable world. They catalogue them. They monitor them. And they only intervene, only make contact, when a civilization reaches a certain threshold of development or when resources are needed. The probes are the eyes. The network is the decision-making system. And we have no idea what criteria they're using to decide which worlds get contacted and which ones get left alone. Or worse, harvested. Here's the uncomfortable question if 3I/Atlas transmits its data back to Epsilon Eridani. If the report includes details about Earth's biosphere, our atmospheric composition, our technological signatures, what decision does that trigger on the receiving end? Do they file us under interesting but primitive, check back in a few thousand years, or do they file us under resource-rich, technologically emerging NED's intervention timeline soon? We don't know. We can't know. And that uncertainty is what makes the March 16th transmission window so critical. Because once the data is sent, once our status is updated in whatever database they're maintaining, we lose the advantage of obscurity. But let's flip the scenario. Let's assume the network isn't hostile. Let's assume it's infrastructure, not surveillance, a transportation system, just like Avi Loeb suggested, a way for information, maybe even matter, to move between stars using naturally occurring trajectories and gravitational assists, if that's the case. If these interstellar objects are buses rather than spies, then catching one, interfacing with one, understanding how it works, could give us access to the galaxy. We wouldn't need to build our own starships. We just need to learn the schedule, figure out the routes, and hitch a ride. Think about what that would mean. Humanity, stuck in the solar system for all of our existence, suddenly able to reach other stars not in 75,000 years, but in 10,000. Still a long time, still far beyond any individual human lifespan. But within the lifespan of civilizations, we could send information. We could send DNA, preserved in digital form, ready to be reconstructed on arrival. We could send art, history, music, everything that makes us human, out into the galaxy, not as a desperate shout into the void, but as a package on a delivery route. The network wouldn't just connect us to Epsilon Eridani. It would connect us to every system those probes visit, every civilization that's already using the network. We'd be joining something ancient, something vast, something that's been operating since before Earth had multicellular life. That's the optimistic view. And it's worth considering, worth hoping for, because the alternative, the idea that we're being catalogued for eventual exploitation, is paralysing. But hope and strategy aren't the same thing. And right now, the strategic calculus being run by governments and defence agencies is based on worst-case scenarios, not best-case ones. They're preparing for the possibility that the network is a threat, that the fragments are forward operating bases, that the transmission is a targeting package. And if they're wrong, if they strike at the object or jam its signal and it turns out we just destroyed our invitation to the galactic community, we won't get a second chance. Civilizations that shoot first don't get welcomed into networks built on cooperation. So here we are, less than 3 months from a potential turning point in human history, and the decision is being made not by philosophers or diplomats, but by engineers and generals, people trained to solve problems, to eliminate threats, to act decisively under uncertainty. Good people, mostly, doing what they think is right. But right depends on assumptions we can't verify. What if the fragments aren't weapons? What if they're seeds, designed to interact with us, to teach us, to upgrade us? What if the orange fireballs aren't dropping surveillance devices, but libraries, archives of knowledge from civilizations that want us to succeed? What if the test isn't whether we can destroy the probe, but whether we can resist the urge to... There's a quote from Carl Sagan from his book Pale Blue Dot that feels relevant here. For small creatures such as we, the vastness is bearable only through love. He was talking about perspective, about how understanding our smallness in the universe should make us kinder, more careful, more willing to reach out rather than strike out. 3I/Atlas is forcing us to confront that vastness in real time. Not as a philosophical exercise, but as a practical decision with consequences we can't fully predict. And the choice we make will say more about who we are, about what kind of species we're becoming, than any data the probe could possibly collect. March 16th, 2026. That's the date. That's when we'll know, or at least begin to know what 3I/Atlas really is and what it came here to do. If you want to follow this story as it unfolds, as the data comes in from the Jupiter encounter, stay close, because what happens next might be the most important observation humanity has ever made. The universe is watching, and so are we. The question is, are we watching the same thing?